Good evening, everyone. This is Vikas Srivastav again. So I hope you all are having a great weekend, right? So this last week we started learning about essential mathematics which are required for data science. So we covered important concepts such as calculus, linear algebra, in which we talked about vector and matrices, and then we also talked about a bit on probability theory, right? I try to give you some intuition on how to build the basic foundations of probability, right? So we started with sets, and then we learned about the counting methods, and then we learned about conditional probability, and then we uh, dove in uh, Bayes theorem, right? So that's a really important theorem, and we'll see how that theorem is applied in machine learning. So I've told you that there is a particular machine learning algorithm which is naive Bayes classifier, which uses the idea of Bayes theorem, and then uh, we also talked about how we can do basic descriptive summary of data, right, using various measures of central tendency, and then there were measures of spread, and finally we also looked at measures of symmetry, right? So uh, in this guided project session, I'm going to introduce you to another very important algorithm, which is sort of very pervasive across different machine learning algorithms. So this is called gradient descent algorithm, and so this is not a type of ML algorithm, but it is such an algorithm which helps in training a particular model, right? So you'll get the idea how do we train a model. I'll try to give you some intuition regarding that, and we'll see how we can implement gradient descent in Python. And so it will be a bit unlike the previous guided projects that you guys have done. So in this session, so it will not be like, yeah, you are following me, but it will more or less be a theoretical in nature, but I'll try to keep it a lot engaging in a way. And then in your guided project notebook, I would encourage you to use some different set of codes to come up with the same set of answers or solution, right? So that will be your task for guided project, and in the self project, that is a sort of an extension of your guided project. So we'll see towards the end what you need to do in your self project. Okay, so let me start with basic definition of gradient descent, and I'll try to tell you how we can use gradient descent to solve a very important problem. So gradient descent is an algorithm which is used to find the local minima of any differentiable function. Okay, so this is really important. So traditionally, how we have been. So can you guys please tell me? I'll just share the Padlet link. Okay, so let's say if I wanted to find the minima of a function, let's say of course differentiable function. So how do we do that? So I'm just sharing the Padlet link over the chat. So you guys can, yeah, use your freedom to tell me what do we actually, how do we actually determine the a minimum of a differentiable function. Okay, so let's say you are given a function fx, and so how do you find the minimum of that function? Okay, so Sriram is saying derivative of fx is equal to 0. Okay, uh, and is there any other condition? So let's say of course I set the derivative to 0, but some people are still writing about the second derivative. Okay, so Sanjita is saying double. Okay, so the double derivative should be greater than 0. Okay, and so there are two things to it. So we'll set the first derivative to be equal to 0. So we'll find the x's for which we get the 0 value. So and then we'll check whether the second derivative is uh, greater than 0 for a minima. Okay, so thanks guys for posting your answers. So let's see, let's take an example of a basic function. So I have in this Jamboard, so let's say I have this function fx, okay, so which is simply x square plus 4x. Okay, so I have this function, and what I want to do, I want to essentially find the minimum of this function. So what I do, firstly, I'll yeah, set the first derivative to 0. That means f dash x should be equal to 0. So in this case, what should be f dash x and dash x? So that will be nothing but 2x plus 4 is equal to 0, right? So we'll find the x is equal to minus 2. Now we can check the double derivative, right? So that is, so double derivative will be nothing but derivative of 2x plus 4, that will give us 2. Okay, and as we can see, this is greater than 0, so this guarantees that x is equal to minus 2 is the uh, is that x for which this function is taking the minimum value, right? And what is the minimum value of this function? So if I write f minimum, so that will be nothing but minus 2 squared plus 4 into minus 2, so that is going to give us minus 4. Okay, and you guys might have already guessed the graph of this function. So we're getting the minimum value at minus 2, and this is an upward parabola if we are right, so something like this, yeah, so at 0 this function is going to take the value 0, because if you plug in uh, 0 to this function, x is equal to 0, so that function will be 0, right? So this is a point here, right? So this function fx is equal to x square plus 4x, and this value is of course minus 4, and this value for which this function is taking the minimum value is minus 2, right? So this is the way in which we find the minimum of a differentiable function, right? So and we have an additional check where we can check the double derivative, it is greater than 0, so that is going to give us the minimum, and let's say if it's less than 0, so it is going to give us the maxima, right? So there can be different nature of right. So let's move to the second frame. So here we can see, so for example, if we have two functions, so one function can be like this, which is what we can call as the downward parabola, right? So this is what we'll call as downward parabola, right? And then and this is what we'll call as, let's say, upward parabola. Okay. Okay, can you guys tell me one thing? Uh, so let's say okay, so for this downward parabola, will for any x will have the let's say, so we'll have this maximum value at for particular x. So in this case, let's assume this x is equal to 0, for which we are getting the maximum of this function. So let's call this function f1x, and let's call this function f2x, right? And so for this function, this particular value is the maxima, right? Or in fact maximum, right? Maxima is the plural of maximum. So this particular value of y, right, this value is the maximum of this particular function. And for this function, if you see, so this particular value of y, this will give us the minimum, right? Minimum of this f2x, right? So this is the general way to use calculus to find out the maximum or the minimum, right? In general, whenever we are equating the first derivative to be equal to 0, and whatever x is we get through this equation, so these are what we'll call as the uh, on for these x we'll get the extrema, right? And one second, yeah, so we'll get the extrema, but we don't know whether this is going to be a minimum or maximum. So we'll need to do an additional check. We'll check the double derivative. If that is equal to if that is greater than 0 or less than 0, so accordingly we'll get the minimum or maximum respectively for that particular x, right? So you get this basic idea, right? So okay, so this is from the theory of calculus. Whenever we want to get any minimum, uh, so we'll basically equate the first derivative to 0, and that will, for that x, will give us the minimum of the function. Okay, so a function can have a lot of local minima, and the gradient descent algorithm will converge to one of them depending on its starting position and learning rate, right? So of course we'll talk about what is starting position and how we define the learning rate. Okay, but before we go into the deep, I'll just try to give you a basic intuition of how gradient descent is used in machine learning, right? So in machine learning, always what we have, whenever you're training a model, so what we'll have, so we'll have some actual values and we'll have some predicted values, right? So let's say we are doing a regression problem in which our dependent variable is continuous. Okay, so it's a continuous dependent variable, so that will call as regression, right? So I can write that particular term. So in regression task, our dependent variable, just think of a particular column which we are trying to model. So that is taking a continuous value. So essentially what we do in machine learning is that there is an x and there is an y, right? So this is why, this y is what we're calling as the dependent variable, right? So this is what we're calling as dependent variable, right? So the goal of any machine learning algorithm is to find such a function f which will give us the mapping from x to y. Okay, so this is the goal of any machine learning algorithm. So this function can have a lot of parameters here, right? So there can be a lot of parameters of this function. So here, of course, I'm taking only two. There can be multiple of them. So the idea is you are given a training data set x, right? And you're also given the training labels, okay, which is the dependent variable. So you're given these two information. So you need to learn the mappings from x to y through this function f, for which we are assuming some set of parameters, right? For example, if you think about a basic linear regression, so in that case, this y is written as, let's say, theta naught plus theta 1 x1 plus theta 2 x2, right? So in this case, based on our x and y, the task of the model is to learn these parameters, right? Theta 1, theta naught, theta 1, theta 2, right? So the goal of the algorithm is to learn these parameters, and this is essentially the gist of any machine learning algorithm, right? So for any machine learning algorithm, the task is to find the optimal set of parameters, so that we can find a mapping from x to y via this function f, right? So now how do you find this mapping f, right? So this is our next task. Okay, so let's move ahead. So in the next what we'll do, uh, so as I was telling you, so we have an actual value, right, which is called, let's say, dv, that is the dependent variable, and we have this predicted value, right? So this predicted value will come from f, right? So for any input x, we'll pass that input into this function f, and that will give us some value, right? So for example, this actual dependent variable is taking the value 10, which is given from our training data set, and in the predicted value, so let's say we assume this f to be, let's assume any functional form. So in this case, let's assume this basic function, right? So theta naught plus theta 1 x, which is the basic linear function in x, right? So if you plug for this, so there is a particular x for which we have the dependent variable equal to 10, and through this function, let's say this f of particular x, we are getting around, let's say, 9.5. Okay, so the actual value is 10 and the predicted value is 9.5. Okay, so now how do we make sure that our predictions are very close to what the actual value of the dependent variable or the target variable is, right? So there's another term for dependent variable, is also called as target variable. Okay, so the goal of any machine learning algorithm is to so we have a loss function which is, let's say, defined as L. So this is a function of, let's say, your uh, dv, let's say, which is the actual value, and we have a predicted value which is coming from a, right? So this a is essentially this coming from dv, and this predicted value is coming from f, right? So of course, here in f we can assume any such thing, right? So for example, it could be, let's say, e to the power theta naught plus theta 1x. There could be a lot of different functions, and different algorithms try to find out or try to map different functions, right? So in linear regression we have this basic function, but if you talk about, let's say, logistic regression, so there will have different f, or maybe if you talk about neural networks, there will have different f. But the idea is we need to learn a mapping from x to y, uh, and what how do we learn this mapping? So these mappings are essentially learned by training, by using the training data and finding the optimal values of these parameters of the function f, right? So the idea is we need to learn these parameters, right? So of course, in this particular very simple case, I have taken this function theta naught plus theta 1x, but there could be a lot of different form, right? So we'll simply write f, let's say theta 1, theta naught, theta 1. It could be multiple thetas as well, depending upon the complexity of the model. So you know that this predicted value is coming from f, and the actual value is coming from the dv, right? Which is given, which is part of your training data set, right? So the idea is we need to find the minimum of this loss function. So this is called a loss function. So this is called as the loss function. So whenever you are training a model, that so essentially what you are trying to do, you are trying to minimize this loss function. Okay. So by minimizing, what do we mean? So we find these theta naught and theta 1 such that the loss function is the minimum, as in so a particular example of this loss function is your RMSE squared, right? So let's say mean squared error, so that can be defined for, let's say, all the observation. So let's say, one second. So let's say this I is, let's say we have n observations, and so here in this case what we can have, so we'll have, of course, the predicted value from f. So this could be fxi minus, and then there could be the actual value for that observation, so we can call that as, let's say, a of xi, right? And we'll square them up, right? So this is the mean squared error, and of course you can put any such factor to normalize it, but that doesn't matter much, right? So we'll of course be focusing on this particular term where our task will be to, so of course we can write this as sigma, and then let's say we plug this particular form which we have written here. So this can be written as theta naught plus theta 1 xi minus, and this could be, let's say, a of xi, and essentially we'll square them up, right? So this is our loss function. Okay. So so in this particular case, so we have this loss function, which I'll just write again. So this is, of course, theta naught plus theta 1 xi minus axi, and yeah, we'll just square them up. So now the task is we need to find the minimum of this loss function, right? So we need to find so what are the unknowns in this particular equation? So the unknowns are theta naught and theta 1, right? So these are the parameters which any machine learning algorithm has to learn, right? So we'll try to minimize this loss function with respect to, let's say, this theta naught, right? And of course we have two parameters here. So we'll try to minimize this function with respect to each of these parameters, and we'll set the partial derivatives to be 0, right? So let's say if you're just working with a single parameter, so there will not use the concept of partial derivative. We can simply write, let's say we have dl, d theta is equal to 0, right? If there were only single parameter. Okay, so the task of, as I told you, so I cannot emphasize this enough. So the task is to learn this function. So when I say to learn this function, so essentially we need to learn the parameters of the function. So what are the optimal set of values for those parameters, right? So essentially, let's say on our for our given x and y, the optimal theta naught could be 2 and theta naught theta 1 can be 5, something like that, right? So uh, our function will in that case will be nothing but 2 plus 5x, right? So this will be our function. So if we want to make any such prediction, so we'll just plug in this x and we'll get the corresponding output, right? So this is what we want to do, right? So we have this loss function. So we have this loss function and we want to find the minimum of this loss function. And how do we find that? We will find the partial derivatives or derivative of this particular loss function with respect to each of the model parameters. So these are what we also call as, in fact, okay, just hang on. So these are also called as model parameters. Okay. So the task is to find these optimal values of model parameters for which the loss function will be minimum. So what does that mean? So when we say the loss function is minimum, that means the error in our prediction, as in the deviation from the actual value with our predictions, that's the minimal across this particular data set. Okay, so this is what the overall gist of training a machine learning algorithm means, right? So this is for any algorithm. If you talk about linear regression, if you talk about logistic regression, or if you talk about SVM, or if you talk about neural networks or decision trees, so there eventually we're learning these model parameters. We're learning model parameters based on our training data set, right? And of course, different algorithms will have different f, right? So in linear regression, of course, I've assumed that this will be theta naught plus theta 1x, but and a different algorithm will assume a different function. So I hope, yeah, you get the idea that what we do in machine learning and what is the task. So for the goal of any machine learning algorithm, I'll just repeat again. So the goal of any machine learning algorithm is to find a mapping between x and y such that we get the minimum of the loss function. Okay, so the loss function is a function of your actual values and your predicted values, and for those model parameters for which this loss function is minimum, that will be our those will be our model parameters. And yeah, so we'll be happy to yeah, go with those parameters, right? Now there's one more concept I want to tell you guys. Okay, so there's one more concept. So there is a notion of parameters and there is a notion of hyperparameters. Okay, of course I'll be discussing about these things in detail when we learn actual machine learning, but I just wanted to tell you, right? So let's say you have a radio. Okay, so you have a radio or a radio like object, just to give you an analogy. So assume that this is a machine learning box. Okay, so let's call this a hypothetical ML box. Okay, and in this box we have a lot of knobs on the outside. Okay, so just like in radio, you have different knobs which you can move around with, right? So this knob you can move around in this particular direction. This knob you can move around in, let's say you can move a particular knob in clockwise direction or in anti-clockwise direction, right? So there are different ways in which you can tune the knob. And let's assume at the top of this ML box, there is a screen, right? So there's a display screen. So there is a display screen, okay, in which what we get, so we are getting the minimum of the loss function, right? So that is being displayed there, right? So of course, this ML box is a relatively complicated object. So from the outside, you only can control these knobs, and that will output you the particular, let's say on this screen, we get the minimum value of the loss function. right? So here we get the minimum value of the loss function. But because this ML box is not that simple, so there is some inner machinery, right? So there could be, let's say, transistors or resistors or capacitors inside it, such that uh, when we control the knob from the outside, right? So when we control the knobs from the outside, what we get, so those changes the internal, let's say, resistance or capacitance, whatever that could be, and that will affect what will be the minimum value displayed outside. Okay, so the knobs that which we can control is called as hyperparameter. The knobs that we can control is called as hyperparameter. Okay, and let's say if I dissect this ML box and I try to see inside it, right? So whatever there could be, so let's say uh, okay, so inside it there could be a lot of stuff, right? And when we control the knobs from the outside, so these things get changed. Okay, so these are called the parameters of the model, right? So parameters can only be influenced or changed with the help of the hyperparameters. Okay, so we cannot control the parameters directly, but we can control them indirectly through what we call as hyperparameters. So essentially, whenever we train a machine learning model, we'll try to uh, tune these hyperparameters or try to control these knobs by moving them around and see for what particular combination we are getting the minimum value of the loss function, right? That is our task, right? So uh, the best model, so what we'll need to do, we'll need to find the minimum of the loss function, right? Or the minimum value of the loss function, right? So this is the basic difference between your parameters and the hyperparameters. So remember, in the case of uh, the function which we assume, so that function which was, let's say, a function of theta naught theta 1, right? So we assume theta naught plus theta 1x, right? So these are the model parameters, right? So we'll not be able to control them directly, but there will be some knobs from the outside that will have access to, and we can play around with them. And once we play around or move around them, we'll be able to change the values of these theta naught and theta 1. Okay, let me see. Some people are okay. So the so I'm just trying to, yeah, give you an analogy. So let's say if you consider an ML box, so it's similar to a radio. Okay, so you have a lot of knobs on the outside. So the you can only, let's say if you wanted to tune into a particular channel, right, on the radio. So what you'll need to do, you'll need to move the knobs around, and that's how you'll get directed to a particular channel on the radio, right? So similarly, here in the case of an ML box as well, we have knobs on the outside that we can control. So these are called the hyperparameters. And then inside this box, uh, by changing these knobs from the outside, we can influence those internal parameters, right? So those internal uh, behaviors will be governed by parameters, right? And we cannot directly control the parameters, but we can do that indirectly through the hyperparameters, which are essentially the knobs on the outside that we have access to, right? So this is the basic difference between parameters and hyperparameters. Now, so how does gradient descent come into this particular picture, right? So uh, through gradient descent, what we try to do, uh, so one important concept, I'll tell you, right? So when we took this particular function fx, right? So we took this particular function fx x squared plus 4x, right? And we wanted to find out the minimum of this function, right? So this function, let's say it's similar to what we also call as the loss function, right? And so in this case, when we wanted to find out the minimum of this particular function, we were able to do it analytically, right? So I'll just write that down so that you get the idea. So we are able to do this analytically. That means we are simply able to calculate the f dash x and equate to 0, and we are able to get the particular value of x for which this function will take the minimum value. But in reality, a lot of functions which different ML algorithms try to learn, right? So they are not solvable analytically, right? So we cannot analytically solve them, or it could be a lot arduous, or it could be a lot tedious for us, right? So what we can do, we can try to numerically solve them, right? So numeric, because we're trying to find the loss function, uh, we're trying to solve this loss function, and will not be able to solve them in most of the cases analytically, but we can do them numerically. Okay, so we have a computer will not be which will not be able to exactly calculate the f dash x is equal to 0, but will be able to reach to that particular minimum through an iterative procedure, right? So numerically, essentially here I will mean that we have some iterative procedure through which will try to arrive at the minimum of this function, right? So so in the analytical approach, we did not we did not even require to use the gradient descent algorithm in the analytical approach, right? But in numerical approach, we can find the minimum of this loss function. We can find the minimum of this loss function uh, by numerically by using this gradient descent algorithm. Okay, so right. So now let's turn back to our notebook here. So, so here you must have been seeing a lot of terms, right? So gradient is there, then of course descent, and then of course optimization. So whatever I have talked about till now is optimization, right? So we are trying to optimize our loss function. Okay, optimize as in we're trying to minimize our loss function, and we'll be able to find some optimal values of our model parameters, and yeah, that will help us solve our task. So there are three important terminologies here: gradient, descent, and optimization. So I want you guys, okay, let me just clear the Padlet here. Okay, so now I want you guys to tell me what you understand by gradient, right? So you have studied calculus, so what do you understand by gradient, right? So is the derivative, is the slope? Okay, so so essentially, okay, I'll just okay, so it's the derivative or slope. So suppose you are given a function like this. Suppose you are given a function like this. Of course, my drawing is not that great here, but let's assume. So let's say this there is a point which we can call as x1 comma y1. Okay, so this is the point we have, and of course this is the y-axis, this is the x-axis, right? So what is the derivative of this function? In fact, yeah, I'll just erase this. Okay. Right. So here what we try to do, we try to, yeah, create a tangent here at this particular point, and let's say this angle is theta, right? So the derivative of this function, so let's call this function as f, right? So the derivative of f at point x1 comma y1 is nothing but tan theta, right? So that is what we call as the slope of the tangent, uh, right? So that is defined as the derivative, and this is what we also call as the gradient, right? So this is also called as the gradient, right? So now we know there are two terminologies out of the three terminologies that we have seen in the notebook, right? So we know gradient, we know about optimization, right? Now we need to understand what the descent means. Okay, so now this thing we do not know yet. Okay, so let's see what descent means. Okay, so when I discuss the algorithm, so you'll get the idea what descent means. But just to give you the linguistic understanding or the linguistic meaning of word or from where this term is coming. So this term is coming, in fact, yeah, I'll just show, right? So this term is coming from the verb which is called a descent. Okay, so descent is basically to climb down. Okay, so the idea is so let's say you have a function. Okay, you start at this particular point, here. And the idea is because this is a function and this is the minimum of the loss function. So this is where you want to reach. Okay, so you start at a particular point, and by calculating gradients in different iterations, we'll try to descend to this particular minimum. Okay, so that is the idea, right? So essentially consider that you have a hill. Okay, you are on top of the hill, or maybe there is a valley, and the valley is the uh, minimum of the loss function, or minimum of the function per se. And what we need to do, we need to descend down or climb down to the minimum of the loss function, right? So from there, this word is coming, which is gradient descent, right? So we are descending through different iterations by calculating gradients, and that is how we are optimizing or minimizing the loss function, right? So as of now, can you guys please let me know if you are able to understand these three terms separately? Of course, I will go through the algorithm in detail. Okay, so yeah, this is pretty basic to understand. Yeah, so you know from calculus what gradient is. That is nothing but a derivative. Optimization, I've tried to explain, that is how, that is essentially in our loss function, or in the context of machine learning, that is minimization of the loss function. And descent is essentially we're descending down from a particular, let's say, point to the minimum of the function, right? So yeah, so I hope, yeah, you guys are clear on the terminology. Okay, so now, so I'll just yeah, walk you through the statements here. So the name gradient descent hints at how this algorithm works, right? So it's plain obvious. So this algorithm requires knowing the gradient or partial derivatives of the function. So that is the first thing. The second is using the gradient to determine the direction of steepest descent. Okay, so we'll use the gradient to determine the direction of steepest descent. So the idea is that we'll begin somewhere on the function. So we'll begin somewhere on the function. For example, f of x1, uh, as I showed you, right? And then we'll climb down the function as quickly as possible towards the first valley, which is the local minimum, right? Where this the derivative of the loss function will be equal to 0. Okay. So the gradient descent algorithm essentially describes the sequence of steps to take to go from x1, that is our starting point, to a local minimum x hat or x star. Okay, so gradient descent algorithm is very commonly used to train machine learning models by minimizing some objective function, right? So I told you the idea of loss function, or what we also call as cost function, right? So that is another term for objective function, and we try to minimize this objective function. And gradient descent algorithm is the algorithm through which we train machine learning models, right? So in this gradient descent, we pass the f, we pass the actual values of the dependent variable, and we try to find the optimal values of the model parameters, which will give us the best model, right? So the best model will be that which will have the least deviation from the actual and the predicted values across all the observations, right? So mean squared error is one such term, right? So that is for regression task, where we have a continuous values of the target variable which we're trying to model, right? So this dv was the y which we were discussing earlier, right? So let's talk about the algorithm intuition. Okay, so I'll not go through the text much, but I'll try to, yeah, tell you uh, through this particular graph, right? So you have this function. Okay, so what you need to do, you start at this particular position a, which is, let's say, your starting point. The starting point could be anything, right? So we pick a random point where we'll initialize or we'll start with. Okay, and then what we'll do, we'll calculate the derivative or the gradient at this particular point. Okay, so that will be defined as del fa, right? So this will be defined as del fa, and then there is one factor here, which is gamma, or what we also call as the learning rate. So that defines how quickly we're able to descend to the another point, right? So let's try to understand this algorithm here. Okay, so Okay, so so we have this function. Okay, right? So let's say I start at this particular x1. Okay, and uh, so what, so this is x initial, let's call this x init or x initial. And so x next, or which is the next x, right? So this is of course your x axis and this is your y axis, and let's call this function as f of x. Okay, so x next, as in let's say this point we call as x next. Okay, so this point can also be called as x next comma f of x next, right? So this is that point, and this point is of course f of x init, right? And this point will call as x init. Okay, so this x init will be given by x, so x next, so the next point which we want to uh, go to, right? So remember, always the objective is to come arrive at this particular point x, right? So let's say this is called the x optimal or the x minimum in this case, right? So this is where we want to arrive to, but we don't know how to do that, right? So we'll start at a particular random point, right, which is called, which we call as x init. Okay, and so this is our gradient descent equation, right? So this is our gradient descent equation, and how this looks like. So x next is equal to x init minus, let's say, some learning rate that we can call as, let's say, lambda, multiplied by the derivative of this function with respect to x at x init. Okay, so this is the equation. Okay, so now let's say for this particular point, you know, can you tell me what is the sign of this particular term? So can you please tell me, let's say for this particular x in it, what is the sign of the derivative or the gradient at that particular time, right? So you can, right? So what is the okay, so what is the sign of the gradient? So Sumanta is saying negative, Sheets is also saying negative, right? Why negative? So if you draw a gradient, if you draw a tangent here, so this theta, right? So if you calculate this particular tan theta, right? So this is going to be negative, right? So so this thing for the starting x in it will be negative, right? So we have a minus here, we have this negative gradient, and of course lambda is a positive term, so this is a positive term, right? So what we'll have in the next, so the next x, so x next will be x init plus some positive quantity, right? So plus positive quantity, right? So x next will be greater than x init, right, in the next iteration. Okay, so in the next iteration, x next will be, so let's say in the first iteration, so in the first iteration, x next is greater than x init. Okay, so now we come at this particular x next or this particular point. Okay, so now in the next iteration we'll of course use the same equation. So in the second iteration also we'll use this particular equation only, right? So here also the derivative is negative, so x next, in fact I should write this as x next is equal to x prev, right? So the previous x minus lambda times the derivative of the function with respect to x at this x prev, right? So here when we are at x next, now we need to find the new x next, right? So it could be, let's say, this particular point, right? So let's call this as x next is something like this, x dash next. Okay, so this will again be given by uh, x next minus sorry, plus some positive quantity, right? So this is a positive quantity, so again, so this x dash next will be greater than x next, right? So here as you can see, so this point, right, so this point is again x next dash, right? So as you can see, so through this iterative procedure, we're trying to reach towards this particular minimum of this function. Okay, so this is what the gradient descent algorithm is, right? So to say or summarize in a layman's term, so what we'll do, we'll start at a particular starting point. Okay, we don't know where the minimum of the function will be, right? So we'll start at a random point. So now I need to find the next x where I'll need to descend to, right? So x next will be given by x previous, that is the previous x which we have, minus lambda or the learning rate. So I'll come to the learning rate, what's the importance of it. So, and then that is multiplied by the derivative or the gradient of the function at the previous x. Okay, so this is how our update equation will be, and we'll keep iterating until some condition is or some convergence is achieved. Okay, so what is the meaning of convergence here? So I'll tell you. Okay, so I'll tell you. So what is the meaning of convergence here? One second. Right, so the convergence will be given by this particular condition, right? So let's say when we are iterating, so the update or the difference between the next x and the previous x, if that is very less than a particular number, right? So let's say in this case this is less than 1 by 1000. Okay, so the update is very small. So in that case, yeah, we'll stop the iteration. Okay, so this will be our stopping point, right? Because this is an iterative procedure. So the natural question is, how do you stop, right? So when do you stop, essentially, right? So when the difference between your x next and the x prev. Okay, so I'll just go to the next frame, right? So we'll stop, right? So okay, sorry. So we'll stop iterating when the update or the difference between your x next and x prev, so that is smaller than, let's say that is smaller than a particular value that we can call as, let's say, epsilon. Okay, so when we are not getting our x's updated by a large margin, so we'll stop iterating, right? So if this is less than some epsilon, so when since the condition is achieved, so we'll stop iterating, and this is what we call as convergence, right? So as in we are very close to the minima of the loss function, right? But of course there are some details, right? So Sumanta is asking that is it possible that it never happens in some cases, right? Of course. So I'll come to these points, but just bear with me. There are a lot of different things, right? Because it also depends where you start and what is your learning rate, right? So now let me come back to the point of the learning rate. Okay, so what this lambda. So I'll just go back to the previous frame, right? So here we have this lambda, right? So we have this particular lambda, and so the larger the lambda, so the larger our update will be. Do you agree with this particular point? So higher the learning rate, so the larger will be update on the previous x. Does that make sense, people? Okay, so the larger the lambda or the learning rate, so the learning rate is essentially defines you how quickly you are descending from the point to the next point. Okay, so let's say you are actually on a hill and you needed to reach the valley. Okay, and let's say you're using the harness. Okay, so of course you can control the control how much meters you want to slide down using that harness, right? So if the harness is quite tight, so you'll be able to slide only by a very small margin. So that means your learning rate or your learning rate is small. But let's say if your harness is loose enough, right? So you'll be able to descend in a quite faster way. So that means your learning rate is quite high, right? So that is the basic analogy, and I think, yeah, you guys are able to understand this particular thing, right? So that is the role of the learning rate. So that defines how quickly, or as in how steeply we are able to descend from the starting point or the previous point to the next point, right? So, and also one more thing. So this particular gradient term, which is the derivative, right? So if this term is also quite large, if this term is also quite large, that means you're even if you have a small learning rate, if the gradient is large, so your update will also be large. Okay, so um, okay, so that's the thing, right? So let's take another example. So let's take another example. So we have the same function, but now we don't want to start on the left hand side, but we want to start on the right hand side. So let's say, let's call this x1, or maybe x naught, y naught. Okay, and of course this is the minima, so let's call this x optimal. So this point is x optimal, and of course this point is x naught, where we are starting, right? So the idea is we want to move in this direction because we want to move to the minimum, uh, minimum of the function. So how we'll arrive at the minimum? So of course we'll need to find the that value of x for which the function is taking the minimum value, right? So in this case, our gradient descent update, that is, let's say x next, will be x prev minus lambda times del f del x, and this will be evaluated at x prev. Okay, so so in this case, let's say we start from here. So here, of course, the gradient is positive because this tan theta is greater than 0. So the gradient is positive, so this entire term is positive. Okay, so in this case, x next will be x less than x prev. Okay, so this means, so our x next could be somewhere here, x next. Okay, so essentially through this gradient descent update, we're trying to move closer to the optimal value of the x. Okay, or essentially what we can also say, towards that value of x for which this function is taking the minimum value, right? Okay, so let me see if you guys no, so Sheets is saying, how do we know that every time the figure is a parabola only? So it's not always a parabola, it could be any function, right? So you can take a cubic polynomial as well, right? It could be anything, but the idea is we should have a convex function, right? So I have not told you about this particular thing, so we should have a convex function. Okay, of course I'm taking the example of a parabola, but it could be any such curve, right? And this curve should be a convex function, right? So convex function is really important. So in the case of a single variable, that is where we are taking the example of a single x, right? Because we are only dealing in two axes here, right? So we have x and we have y, right? So in the case of a convex function, our Hessian, or in this case, in this simple case, our double derivative, which is this, is greater than 0. Okay, so that is how we'll get the minima, right? So uh, so this is applicable only for convex function, and in most of the machine learning algorithms will be optimizing convex functions only, right? So convex functions are, because for convex functions are similar like this, right? And if you're talking about a concave function, so there's something like this, right? So this is convex and this is concave. Okay, so this is just an example, but let's say if you're dealing with multiple variables, so there this is not that easy, so we need to calculate what we also call as Hessian matrix. So once we have this Hessian matrix, we need to make sure that this Hessian matrix is positive semi-definite, right? So of course you don't have to worry about this at this particular point of time. A positive semi-definite essentially means that all the eigenvalues of this particular matrix, they are non-negative. Okay, that is the only meaning of this positive semi-definite matrix. Okay, so I think you know about Hessian matrix, right? You taught in the calculus class. Can you guys confirm once if you know about the Hessian matrix, or right? Have you seen this? Okay, no worries. Don't you don't have to, yeah, worry about this, right? So essentially, the Hessian matrix is the Jacobian of the derivative. Okay, so don't have to worry about it. So just you can keep this in mind. Even if you forget, that's fine, because we'll be taking this up at later point of time. Okay, so whenever we are talking about gradient descent algorithm, we'll assume that the function that we are minimizing is a convex function. Okay, so we'll assume the function which we are minimizing is a convex function. Okay, does uh, does that make sense, everyone? Okay, 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 perfect. So I think, yeah, you guys are able to understand. So this is what the algorithm is. Okay, so now we understand the overall working of the algorithm. So now we can see what are the shortcomings or what are the limitations of this particular algorithm, and you'll get an idea of what kind of trouble that we can run into, right? So okay, so okay, now there's really important concept, right? So let's say you start at this particular point. Okay, so in fact I'll just yeah, add one other frame, and here I can write for you guys. So let's say we have a particular function like this, right? So let's say if we start at here, right? So of course our initial point is random, right? So we initialize at a particular any particular point, right? But so you know that your gradient descent equation is this, right? X next is equal to x pref minus lambda times the derivative of this function, right, with respect to x evaluated at x prev, right? So this is very important, right? So this is a very important question that can be asked in your data science interviews, right? So uh, they'll ask you, explain me the gradient descent algorithm. Okay, so when you write the gradient descent update equation like this, right, so you need to say that, yeah, this function uh, will be evaluated at the particular x prev, right? Of course, in context of machine learning, in the case, so here will not have x's. In the case of machine learning, when I talked about the model parameters, so there what will have the theta nu. So let's say there is only one parameter with the model, right? F theta. So there what we'll do, theta nu is equal to theta prev minus df d theta evaluated at theta prev. Okay, so of course in this case this function was a function of x, but in the case of machine learning our loss function will be nothing but a function of theta, because the dependent variable is known, that value is known, and the function is in the form of theta only, right? So the only parameter that we have, or the only unknown or variable that we have, is theta. So using the gradient descent, we'll try to update the uh, or learn those parameters for which that function is taking the minimum value, right? So in the case, let's say if we have theta, so this axis will be theta. Okay, so do not get confused. I am just taking x here for example, but in the case of machine learning, this x will of course be replaced by theta, that is your model parameter, right? So on the x axis we'll have the model parameters, right? And remember, we will not be able to control the model parameters directly. Okay, so during the training, what we need to do, we need to control the knobs, which are your hyperparameters, and that will eventually run the gradient descent algorithm in the back end, which will try to come up with the optimal values of these thetas, and that will help us generate the best machine learning model on that particular data set. Okay. So someone is asking, lambda will also affect accuracy. Of course, yeah, lambda can affect, right? So lambda, this learning rate, this is a hyper parameter, because we can control what should be the learning rate, right? So learning rate, that is lambda, can be 1, it can be 0.1, it can be very small, 0.001, so it can be anything, right? So it can be also 10. So we have to experiment with different values of lambda and see for which. So lambda in this case, so of course lambda is a hyperparameter, so that will have the freedom to control. Okay, so this is a hyperparameter. Okay, so I just digressed a bit, but I just wanted to tell you one important point here. I'll just erase most of the stuff here. In fact, I'll just clear the. Okay, in fact, yeah, I'll just. Okay, so this is our. Okay, so let's say this is our f, or f of theta, or f of x, whatever you can call. Okay, so let's say if we start here and our lambda is very high, so let's say lambda is greater than 5, so greater than 5 is quite high. So what we can do, so what will happen in cases of large learning rate? So in cases of large learning rate, so let's say this was the ideal x next that we could have come up with, right? So this was x prev and this was your x next, right? But in cases where your lambda is high, so what will happen? So rather than jumping to this particular point, you might be able to overshoot your minimum, right? So it's possible, right? So you might go in the other side of the minimum, right? So there you will just, for high learning rate, you will just keep going here back and forth, something like this, right? So because the update, this particular term, right, this particular term, right, for large lambda, what will happen, this particular term will be large, so the update will also be large. So it might be possible that rather than arriving at this particular x next, what will happen that you'll reach at this particular point, right? So in cases of large lambda, it might be possible that you're just moving back and forth here, you're just moving back and forth here, but you're not able to descend to the particular minimum, right? So that is very critical for the convergence. Okay, so you know what, how do we define convergence? So if our x next and the difference between the x next and previous is less than an epsilon, which in our case, let's say this could be very small, 1/1000, something like this, or you can control that as well. Okay, so if this is really small, so that means the update is very small, and there will say that yeah, we have achieved convergence. But in cases where our learning rate is quite high, so this update will be quite large, and so will be what will happen, that will overshoot the minima that we wanted to arrive to, and will not be able to converge actually, right? So there are some things which you need to be cautious of, right? Okay, also there is one more thing. So in case where, let's say, you have large lambda, so you might be able to overshoot the minimum. Also in the case of very small learning rate, so your updates will be very small, so it might happen that you get stuck in a particular local minima, right? So it might be possible here, right? Because a function like this, they can so this is a local minima and this is a global minima, right? Our objective ideally would be to arrive at this particular global minima, but let's say if we have a very small learning rate, so we'll not be able to reach this particular point, right? So that could be a case. So Smriti is saying that, so theta is general convention for model parameters. Don't we need different learning parameters for different model parameters? The scale could be different. Okay, so essentially, see, different learning algorithms will have different parameters. As in, let's say you denote the model parameter by theta, but that functional form or the f theta, that can have different forms, right? So that is what will differentiate from one ML algorithm to another ML algorithm, right? The form of the f theta, right? So in the case of linear regression, that form of f theta will be, let's say, theta naught plus theta 1x, but for, let's say, neural networks, that could be some different form of the function, right? So I hope, yeah, you're able to understand that. So when LR is very small, we might get stuck in the local minima instead of global. Yeah, that is what I wanted to, yeah, point out here, that there are some problems with very large learning rate or very small learning rate. Okay, so essentially what you will need to do, you'll need to experiment with different learning rates and see where you're getting the best performance. So best performance will be judged by uh, uh, the error which you are getting, right? So when you get the, let's say, mean squared error in the case of regression task, so you get, you sum up the mean squared error across all the observations, and if you get that to be very the least for a particular learning rate, so that means, yeah, that learning rate is giving you the optimal set of, so that is giving you the optimal model. Okay. All right, so this is what the gradient descent algorithm is all about. Okay, so just before I move ahead and yeah, we do the implementation, can you guys please confirm once if you are able to understand the gradient descent algorithm, because this is a really important topic, right? So yeah, I just want to hear yeses from most of all the people. If you have any doubt, do let me know. I can go walk you through again. And so Smoothie is saying that, I mean, for same ML algorithm, don't we need different lambda value for different model parameters, theta such as theta 1, theta 2? No, so you don't have to get confused. So for a single, let's say, implementation, so let's say we are implementing the linear regression algorithm, and we are doing that numerically, not analytically. Of course, there is a analytical approach if you go through the statistic side of things. So there is a solution for linear regression which you can get in a matrix form. But let's say if we try to solve the linear regression problem using the numerical approach, that is using the gradient descent. So there, let's say the model has two parameters, that is theta naught and theta 1, but of course we'll have only one lambda for a single implementation of the model, right? So it will not be such that you have lambda for particular theta naught and for particular theta 1, right? So I'll come back to the point where instead of single uh, parameters, we have multiple parameters. So I will see how we can do multivariate gradient descent, right? So here, of course, we're talking about a single variable, but I'll tell you how we can write the gradient descent update for multiple parameters as well. Okay. So yeah, just don't get confused here, right? So there will be a single lambda or single learning rate uh, for a single implementation, right? So in single implementation, that means when we train that model, we'll get a fixed value for theta naught and a fixed value for theta 1 if you're implementing a linear regression. Okay. So, okay. So of course, as I told you, there are few caveats of the gradient descent algorithm in terms of how we choose the learning rate. So if the learning rate is large enough, we'll overshoot the minimum and we might not be able to actually converge. And let's say if you have very small learning rate, so what might happen that we can get trapped in a local minimum and we might not be able to actually converge or get to the global minimum. Okay, so there, yeah, so that is the caveat associated with the gradient descent algorithm. Okay, so I think, yeah, you guys understand this. So for single variable, this is the gradient descent update equation which I have told you, and this is the point of convergence, right? So because this is a numerical approach and we are iterating, right? So essentially what we are doing, so I can, yeah, walk you. So let's say uh, so so in the first iteration, so let's say we start at x sum x naught and our function is, in fact I'll not use the terminology x naught, I'll use theta naught because you might get confused with x as the training data set capital X, right? So I don't want to confuse these guys. So let's start with sorry uh, so let's start with theta naught and this function f of theta, right? So here, so theta naught is our starting point. So in the first iteration, so theta 1, that is our new theta, will be theta naught minus lambda times df d theta evaluated at theta naught, right? So this is the first iteration, and we check if theta 1 minus theta naught is less than epsilon. If this doesn't happen, so we'll move to the second iteration. Okay, so now in second iteration, theta 2 will be equal to theta 1 minus lambda times df d theta evaluated at theta 1, because this theta 1 is the theta prev notation which we have been using, right? So here also now what we do, we'll check theta 2 minus theta 1 if this is less than epsilon, and if this is not the case, we'll move on to the third iteration, right? So so in similar way, we'll keep on iterating until we get some theta n minus theta n minus 1 less than epsilon, right? So once this is achieved, so this is what we'll call as convergence. Okay, this is what we'll call as convergence, as in the algorithm has converged and we have been able to find the minimum of the loss function, right? So once we have that, so that particular theta n, so here of course I'm talking about a single parameter model. I'm assuming that this function has a single parameter, right? So in this case, we'll see that say that theta n is the uh, optimal parameter. Okay, so our function, so our optimal function, or the function through which we'll of course make predictions, or the model will be nothing but a function of if you plug in theta n, so that will be right. So theta n will of course be a value, and you need to understand that theta, when we write theta, so this is a general notation because this is a variable, but when I talk about theta n, so theta n takes a specific value. So it takes a value based on whatever we are getting from here, right? Based on whatever we are getting from here. So yeah, Sriram is asking why we chose 1/1000 as threshold. So of course you can play around with the threshold as well, right? So you can have, instead of 1/1000, you can have 1/100, or you can have 1/10,000, or 1/1,000,000, something like this. So that depends upon you. But I think 1/1000 is a reasonable enough value of the epsilon, or the update, or right. So let's say the difference between your new x and the old x, or the new theta and the old theta, if that is very small, so that very small is we are defining by 1/1000, which is a reasonable enough approximation, but or assumption. But of course you can take it to be smaller than that, right? So that depends upon you, right? But I think 1/1000 is a good choice, right? So let's say, so for theta naught, let's say you get a value like 0. So let's say theta n minus 1 is 0.256. Okay, and this new theta n you get 0. So let's say this is something like this, and you get something like 1 to 1, something like this, right? So here we'll see the difference, and if this difference is less than 1/1000, so we'll say that yeah, these two values are almost same. That means the update is not happening at all, right? So you can say that theta n minus 1 is approximately equal to theta n, right? So there's hardly any update, and we can say that yeah, at this value we'll be getting the minima of the function. Okay, does that make sense, Shriram? Okay, perfect. Okay, so now let's quickly go through the implementation. We'll not spend much time, but before we go through that, we'll discuss the case of the multiple variables here as well. Before yeah, I dive into the implementation. So in the case of multiple variables or multiple model parameters, so we'll need to have this particular form, right? So I'll just yeah write this here. So let's say your particular ML algorithm, yeah, your particular ML algorithm has multiple model parameters, right? Theta 2, theta 3, right? Till theta n maybe. So in in the case of multivariable, so in the case of multivariable gradient descent, so what we'll have, so this equation will be, let's say So similar to what we have seen here, so it will be, let's say I write this theta naught and n plus, let's say I call this n plus 1. N represents the iteration. Okay, n represents nth iteration. Okay, so we'll have n plus 1 theta 2, or maybe uh, I'm just using some confusing terminology. I'll just fix this. Maybe let's call t for the iteration. Let's reserve that term, right? So t plus 1, so t corresponds to tth iteration. Okay, so theta naught t plus 1, theta 2 t plus 1. Similarly, you will have theta n t plus 1. So we are assuming the model has n model parameters. So this update will be given by this particular matrix equation. So remember earlier we were just having this equation, but now uh, in the case of multi-model, in the case where our model has a lot of model parameters, so we'll need to update all these parameters at once. Okay, so theta naught t, theta 1 t. Similarly, we'll have theta n t, and then this will be lambda times d f d. So of course, this will again be a matrix, and lambda is a scalar multiplied to this matrix. So of course, this will be multiplied to each of the term. So this will be d theta at theta naught t, df d theta at theta 1 t, df d theta at theta 1 theta n t. Okay, so this is the update equation we have, right? So as you can see here, so in the case of multiple variables, what we need to do, we need to update these equations simultaneously. So that means we'll need to solve this or update this uh, at once. So in this case, how do we define the convergence? So the convergence, remember in only in this case of single parameter model, so the convergence was defined in this case, but in the case of multiple variable, the convergence will be defined in this particular uh, uh, equation, right? So let's see that, right? So in this case, what we'll have, so root under, so uh, theta naught t plus 1 minus theta naught t, so we'll square this, right? So we'll do this we'll do the summation for, and this value should be less than epsilon, right? If we had only single theta, right, so there will be no, these terms will not be there, so only we will have this particular term in the case of single, and the root and the square, they will cancel out, so that's why you're just having the modulus, right? So modulus theta naught theta n t plus 1 minus theta naught t, that is less than epsilon for the case of single variable, right? So let's say if we had just this particular term, so that will reduce to this particular case. Okay, does that make sense, everyone? In the case of multivariable, yeah. So Kirtana is asking, does all model parameters get optimized the same iteration? So yes, yes. So yeah, they will get, because this is a matrix equation, right? And yeah, so all the updates will happen at the same time, right? So T denotes the tth iteration. Just keep that in mind. So once we are writing in the form of T, that means all these equations are getting updated at the same time. So if we look at all the equations that we get from this matrix equation, so I'll just tell you here. So that means what we have. So let's start with theta naught. So theta naught t plus 1 is equal to theta naught t minus lambda times this blah blah, right? So evaluated at theta naught t. So this is of course one equation. Then of course for the other model parameter, you'll need to do the same thing, right? So this is the second equation. Of course, I'll just write this for clarity here at least. Theta 1 t. Similarly, yeah, so we'll have n set of equation because let's say there are n model parameters. So, and this is the equation for the tth iteration, right? So at the tth iteration, we'll calculate, right? So this is the nth equation, right? So all these n equations, they will be yeah, updated simultaneously because we are at the TS iteration only. Okay, does that make sense, everyone? Yeah. Okay. All right. Okay. Perfect. So now let's see how we can implement a basic gradient descent. And okay, so let's see how we can implement a basic gradient descent in Python from scratch. But when you actually use the sklearn functions of machine learning algorithms, so this so they are also being solved numerically. So there, of course, you don't have to write the code for gradient descent because that is already written in the package. So they're already written in the function, so you don't have to, yeah, think about those. But it's nice to yeah do work out a problem in which we implement the gradient descent from scratch, and that will help you develop your notion. Okay. Okay, so so now in yeah, so in our Python implementation, I have taken this function fx is equal to 0.1 x square plus sine of 0.1 x square. Okay, so this is the function which we have, and we need to find the minimum of this function using gradient descent, right? So of course, we don't want to go through the analytical route. We want to go through the numerical approach, and that is where we'll be using the gradient descent algorithm, right? So gradient descent requires us to compute the first derivative, which is f dash x is equal to 0.2 x plus 0.2 x cos of 0.1 x square, right? So this is the derivative of this function f. Of course, in the analytical approach, you would equate this to 0 and then find the all possible set of x's for which f dash x is equal to 0, and that will give you the minimum or whatever you want, or the extrema, right? Uh, now, okay, so now because we want to implement the gradient descent approach, so of course we need to know the gradient, right? So we need to know the general form in terms of x here, and well, let's see how we can do this, right? So here I'm importing from numpy everything, and also from matplotlib.pyplot I'm importing everything. So let's just run this. Okay, so here I'm defining my I'm writing a function which I'm calling as f, and this function is taking the argument or input as x, and it returns this particular function, right, which I have written here, right? Now I have written another function which is plotf, so which is nothing but just to plot the function, right? So this is you don't have to worry about it much. I'll just skip this, but I'll just run this and show you what this function gives us, right? So this function is essentially this particular function that we have defined up here, right? So we are just plotting this particular function here, and the range of x is basically from -10 to 10, and okay, so this is how this particular function looks like. So as you can see, so here of course we don't have the local minimum, but it is what we call as a saddle point, right? So here it's neither the local minimum or the local maximum, but it's a saddle point, right? So as you can see, this function is symmetric. Yeah, so this symmetric across x is equal to 0, right? So yeah, if I just use the annotator, so this function is symmetric across x is equal to 0. Okay, x is equal to 0, but nothing but the y-axis, right? Okay, right. So this is the function which we have assumed here. Of course, uh, in your, let's say, gradient descent implementation, you can for starting you can assume a similar set of function. Just take a convex function, for example. Okay, so this looks like a convex function, and we are happy to go with it. Okay, so notice that the function has global minimum at x is equal to 0, but there also seems to be two local minimum. Rather than the local minimum, we'll say that, yeah, these are the saddle points, okay, at -5.5 and 5.5. Okay, so let's call them local minimum just for comparison's sake, but we know that, yeah, these are saddle points. Okay, and you know that the range of x is -10 to 10 here, and this is how the function looks like. Okay, So now I'm writing another function which is essentially the derivative, right? And we takes the argument as x, and it is this particular derivative, right? There is a functionality in SciPy library where we can actually calculate the derivative as well, right? So we don't even have to specify this beforehand, but for the simple example, we know the derivative, the general derivative form. So that's why I have written another function which is derivative x. Okay, so let's run this particular function. Okay, so so up till now, what we have done, we have created a function which creates our function fx that we have defined here. So we have created a function which basically returns this particular function value for any x. We have so yeah, we have seen how this function looks like. So where is the global minimum and where are the local minimum, and then we also have written a function for the derivative. Okay, so we have also written a yeah, so this is a univariate, right? This is a univariate. In your self project, you're going to implement a bivariate gradient descent, but the idea is very similar, right? So I told you right here. Uh, so in the case of, right, so a single univariate, so we have this form, but in the case of multivariate, you'll need to solve this particular thing, right? So because you're aware about the numpy functionalities, so you can play around with the matrices. So these things are pretty straightforward, right? So that will be your task for self project. Okay, does that answer your question, Siege? Yeah. Okay, perfect. So now next, what we'll do? So now we have written the derivative. So we have at this point everything. So all the ingredients we have that we can plug in into our recipe for the gradient descent, and we'll be able to come out with the best meal. Okay. So we'll write a function which is grad descent, that is short for gradient descent, and this function will take three inputs. One is the derivative, which is the function. Of course, a function can be an input to another function, right? So this is the derivative we have. We have x pref, which is to denote the initialized x, okay, and the learning rate, okay. So because in this case, we need to provide to this function where we want to start with, or where we want to start off, right? So that will be supplied here in xprep, and we also need to provide what is the learning rate that we are going to use. Okay, so of course we'll play around with different values of learning rate. So this is what I have kept as a function argument. Okay, so now first things first, we will define when to stop the algorithm. So epsilon, I'm just defining here as 1/1000. Okay, and so there is one counter I have created, which is short for the number of iterations. So grad iter. So this is one. So this will define the first iteration, and then we'll keep updating that as soon as when we have more and more iterations. Okay. So let's move ahead. So now we need to update the x's. Okay, so how do we update? So this is the gradient descent update equation that we have learned earlier. So x next is equal to x pref minus the learning rate times the derivative evaluated at x pref, right? So this is what we have here. So any confusion at till this point of time, guys? Do you have any confusion till this point of time? Okay. 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 All right. So I think, yeah, you understand. It's pretty straightforward. This is what we have, right? So this is the gradient. In fact, I'll just write this. So this is the gradient descent update step. Okay. So x next is equal to x pref minus the learning rate times the derivative evaluated at x pref. Okay. Now what I'm doing, I'm creating an array which I'm calling a sequence, and this sequence will store all the x's that will get at each iteration. Okay, so we're going to create an array. Okay, because we want to see what are the x's which are getting, right? So essentially, I'm creating an empty array here, and here I'm appending firstly x next. Okay, so now this is for the first iteration. Okay, so this is for the first iteration. Now we need to write the condition for convergence, right? So here what we'll do, we'll yeah, keep doing iterations when this is true, right? So when this condition is true, we'll keep doing iterations. When this condition is false, we'll stop doing any further iteration. Okay, so this is nothing but the convergence equation, that is essentially the difference between your x next minus x pref, that is greater than epsilon, right? So in this case, while this is true, right, so here of course this is greater than, not less than, because while this condition is true, then only all these things will be executed. When this condition is false, that is the update term that falls below the epsilon, then we'll stop iterating. Okay, so hope you are able to comprehend this. Okay, so now what we'll do, will so x prep, I'll update this to x next. Okay, so I'll assign the value which I have gotten in x next will be assigned to x prep. Okay, because we want to have the last thing, right, which will essentially come from the x next of the last iteration. Okay, now of course we'll keep updating. So x next will be equal to x prep minus learning rate times the derivative evaluated at x prep. Okay, and in the sequence, of course, we are going to append the x next, because we want to have this array of values of x next. So what are the x's that we are getting for each iteration? Okay, and then I have another statement where I'm just updating the number of iterations. Okay, so how much iterations are we taking to finally reach the convergence? Okay, so this is a helpful counter that we have here. Okay, so any confusion here, of course, there is. So you'll ask that we have this particular equation here, but also here. So the thing is here, of course, this update equation is only done once, but now next, we'll check for the convergence thing, and we will keep on doing the iterations. So does this particular function make sense, guys? Okay, perfect. So all right, so now here we are returning a tuple of 3 elements. Okay, so here now we are returning, of course, it's optional to provide the parenthesis, but so the first tuple element that we are returning is x next, that is what is the final x that we are getting, right? Then we have the sequence of x's that we are encountering when we are doing the iterations, and of course the third is the number of iterations that we have taken to reach the convergence. Okay, so let's run this particular function. So now I have run this function. So I'll store the output of this function. So this function takes 3 inputs, right? The derivative function that we have defined above. Then the second is we need to provide the x prep, that is the starting point where we want to start. Okay, so that will provide. Okay, so let's say we start at x is equal to 8, because we know that the range of x for which we have plotted the fx was between -10 to 10. So let's let our starting point be x is equal to 8, and our learning rate, let's keep this to be 1. So I told you that the notation for learning rate is lambda, but a lot of other texts, they deal with the Greek letter alpha to denote the learning rate, right? So once you are clear that alpha, either you can say alpha or lambda, but once you know that that represents your learning rate, that's fine. Okay, so don't get confused, right? Of course, you can denote a particular quantity with any Greek letter you want. It could be anything, but you need to be just sure that what is it. Okay, so here the inputs are derivative, the starting point is 8, and the learning rate is 1. And here what we are plotting, so x, so we have the x from here, right? Remember, x is this particular bit which is between -10 to 10 at an interval of 0.1. Okay, so that is our x, and we are plotting the gradient output and the index we are applying 1. That is the second element. So that is essentially the sequence. Okay, so sequence is again the array of the same number of elements. Okay, so let's go ahead and run this. Right, so now as you can see, so we started at let's say 8. So we started at this particular point. Of course, this is not shown here, but I can denote it here. Maybe, yeah. So this particular point, right? So this is the starting point. So we started here. Okay. In the first iteration, 1 second. Right. So in the first iteration, what we did, we descended at this particular point in the first iteration. Okay. So we descended at this particular point. In the second iteration, we descended to this particular point. In the third iteration, we descended to this point. In the fourth, we descended to this particular x, then this, then this. So we kept descending until we reached the minimum. Okay, so this is what we have, right? So now we can actually print a grad output, right? So grad output 2 gives you the number of iterations, right? So we took around 20 iterations to converge to the minimum value of this particular function. I'll just delete this particular thing. Now we can also check grad output 1, which is what we have plotted here. So grad output, right? So grad output 1. Let's see what this contains now. Right, so this contains these values. So now, as you can see, so these are essentially your x's, right? So so the at the end of first iteration, the x took the value of 4.8, which is this particular point. Then it took the value of 4.5, which is this particular value. Then it took the value of 3.99, which is this value. Then 3.21, which is this value, right? Similarly, so we kept descending. So okay, so all right, and then finally we arrive to 1.1 into 10 to the power minus 3. That is a very small value and very close to 0. Okay, so we are at this particular point of time. So as you can see, the difference between these two is less than 1 by 1000, and that's why the algorithm converged in only 20 iterations. Okay, so this is what the gradient descent implementation looks like for this particular starting point, which is x is equal to 8, and this particular learning rate, which is 1. Okay, so any confusion till this particular point of time? Guys, can you let me know over chat any particular confusion if you have? Okay, so this particular implementation is clear. So now we have written the gradient descent function. So now we just need to plug in different values of starting point and different learning rates to experiment, right? So now we will just be doing experiments. So here what we'll do, so we'll use a smaller learning rate. Okay, so here of course I'll start at -8, and my learning rate is going to be 0.1, and here of course I'll just update this to be 0.1. I'll just call this lambda because that is what we have been using, and starting point is -8. Okay, so let's go ahead and run this. So here of course I started at -8, and see, I got stuck in this particular point. Okay, so the algorithm converged here, but as you can see, so we got stuck in local minima, right? So we're not able to descend here. But let's say if I started at -5, so what would happen in that case, right? So in -5, as you can see, if we start at this particular -5, so we'll take a lot of iterations because this is full of blue values, and but we have eventually converged to this minimum, right? So small learning rate will take a large number of iterations to reach to the minimum. But there is a caveat associated with it, because if the starting point is, let's say, it's not well defined, or if it's right, so we can get stuck in the local minima, right? So now let's see the output. So grad output is there, right? So how many iterations we took if we are using the learning rate, right? 0.1, so 155 iterations, right? Earlier, let's say in this particular case, if I started at 5, let's see if, right? So here grad output 2 will be 20, right? So we're only taking 20 iterations to uh, descend from a particular point to the minimum, right? But in the case of small learning rate, we are taking a large number of iterations. Okay. Okay, so I'll just yeah, come back to your question sheets. Yeah, just give me a moment. Okay. So now what we can do, so here we started at -5 and zero point 0.1. Okay, so now we'll take another example. So this is what we did actually, right? So this is what we have had here, right? And of course you can experiment with different set of values, and you'll get the corresponding, right? So let's say I start at -5 and my lambda is quite 10. It's pretty high. Okay, so I have very large alpha, or sorry, lambda. That is our learning rate, and our starting point is, let's say, -5. So let's see what this gives us, right? So here, as you can see, yeah, so it kept rocking back and forth, right? And finally, yeah, let's see what's the output it has. So grad output, let's say 0. So this is your, right? So this is sorry. So 49 iterations, and we can check our the array of x next, right? So as you can see, here we were at -6, then it crossed the minimum and went to the positive side, then it, yeah, descended to 2.2, and then it rocked back to the negative side, right? So here, as you can see, it just kept rocking back and forth till it descended. In fact, so this is not the minimum, in fact, right? So as you can see here, the update is very small. So essentially what happened, that it got stuck in this local minima only, right? So if you are using the large learning rate, right, so that will, in most cases, it will not get us to the global minimum, right? So are you able to appreciate this basic fact? So where we can play around with different values of the learning rate and how that changes the guarantee for convergence. So can you please let me know if you are convinced by my point? Okay. So can you explain the saddle point by code where the code stuck? Okay. So here essentially what happened. So maybe I'll just use the annotator so that yeah. So one second. Yeah, let's keep it in this way. So have a look at this, and let's have a look at this. Okay, so I'll just use the spotlight to help you, right? So where did we start? So we started at minus, let's say we started at where did we start, in fact? Let me just check. So we started at -5. Okay, so we started at -5. So what happened, right? So we started at -5. So in the next iteration we went from -5 to -3, right? So we went from this point to this point. Okay, next, in the next we went to 6.77. So from this -3 we went to this particular point, which is 6.77. Now at this point, in the next iteration we went to -4. Okay, so in fact I can use the pencil as well. Sorry, give me a second. Right, so we started at somewhere here, we moved here, right? So we moved here, then we moved here, right? Then next we moved to -4.4, right? So we moved somewhere here, then next is 2.91, right? So next we move to this particular point, let's say, or maybe at this point, right? So essentially, we kept rocking back and forth until this got stuck here, which, as you can see, so 5.616 and 5.615, right? So here the difference or the update, which is, let's say, x next minus x prep, here it is less than the epsilon that we had defined, and that's why it got stuck in the local minima here, right? So here we are not able to reach to the minimum, right? So does that answer your question, Aman? Right. So while condition, so here essentially what happened, I'll tell you. So let's look at our equation. In fact, I'll just clear out the drawing. Okay. So let's have a look at the equation. So here this condition went negative, as in the requirement for convergence was fulfilled. So it stopped iterating. So here uh, we are not able to reach to the global minimum, but uh, it got stuck in this local minimum here, and there the condition of convergence was satisfied based on our criteria that we had defined using epsilon, right? So that's why we are seeing this particular bit. Okay, so this is all about gradient descent. So there are few things. I'll just read it down. You are already aware about this. So from the above exercises of changing the initial value, so it's also very important where you start, right? So there is no fixed recipe as in where you want to start, because you don't know where the global minimum is, right? So of course you'll need to pick a particular starting point that will be a randomly initialized point, right? So you don't of course you can take a heuristic guess at it, but essentially what you'll do, you'll pick a, or you'll make a random guess, right? So you can use this function, let's say uh, np dot random to start with the initialized point. Okay, so you know that based on so in our gradient descent algorithm, there are two things which are critical. So one is where we are starting, what is the starting point, and what is the learning rate, right? So based on the combination of these two values, we saw that gradient descent is not guaranteed to converge to the global minimum, right? So even though the function which we had was convex, but there we had the saddle points, and there our for some cases the gradient descent algorithm got stuck. Okay, so having a really low learning rate can make convergence slower, right, and make it more likely to get stuck at local minima. This is what we have seen. So really low learning rate will make our convergence slower, as in we'll need a lot of iteration, and it's very likely that we'll get stuck at local minima. A very high learning rate, on the other hand, may be even more problematic, as the gradient descent may never converge, right? And the initial value is also important for finding the global minimum, right? So let's take an example of mine. Let's start at -5, and let's put 6, maybe. Yeah, so yeah, here see it's running, right? So the while condition is not the algorithm is not able to break out of the while loop, right? So this is essentially an infinite loop in a way, not infinite, but it's a lot of iterations, right? So here it's essentially it's just rocking back and forth or in your hill, but it's not able to descend down to the global of the minimum, right? So that's why it's running, right? So it's not able to yeah, get out of the while loop, right? So we'll just, yeah, stop this here. Okay, so maybe I'll just keep this to one at this, yeah. But of course, yeah, this you can experiment around with different values of lambda, right? The initial value is also very important for finding the global minimum. So if we start close to the global minimum, we're more likely to find it in the above example, right? So this is the case, but of course, in complicated cases, you'll not know what is the minimum value of the loss function, right? Or it can be, or maybe you'll not know for which theta you'll get the minimum of the function, right? So that will be a lot trickier. So you'll just need to make a randomly initialized guess. Okay, so yeah, so these are the caveats. So I think, Sriram, you can keep on printing the x next for lambda is equal to 6 and see if you are getting the x next or not, right? So that is one way to confirm your hypothesis or disconfirm. Does that make sense? Right. So uh, it does not have 6 variables, but it essentially, the value of lambda is 6, as in it has higher value of lambda, right? So that's why it's not able to converge. So it's not 6 variables. We're still dealing with. Okay, okay, okay. Sorry. Okay. Yeah, I'm really sorry about that. Okay. So now we have understood how the gradient descent algorithm works, and we know the caveats of the algorithm as well. Now let's talk about the minimizing multiple variable function, which you guys will be doing in your self project. Okay. Okay. One more thing, because in this guided project you're not doing anything, so I request you guys to write another function, right? So you don't have to use this function, right? So write your own function and then submit your notebook. Okay. So I'll let you know the deadline, but you should write your own function for the gradient descent. Don't write this, right? So you can make this much better, in fact, right? And you can have a lot of nice plots as well, right? So you can also try modifying the plot f. So that will be your guided project assignment. Okay. So now let's look at finally how we can minimize multiple variable equation at once. Okay, so this is an equation in 2 variables. Okay, so let's yeah, move to the 16th frame here. So I'll be sharing the PDFs with you guys, so you can go through the equations from here as well. Okay, so let's assume a function. So I'll not use x or y because I don't want to get you guys confused. So I'll just stick with the term theta naught and theta 1. Okay, so let's say we have this equation, which is theta naught squared plus theta 1 squared plus 1. Okay, so so in this case, how do we find the minimum of this multivariate function? Okay, so this is an example of multivariate. In fact, to be precise, this is a bivariate. Okay, so how what do we do in this case? So we find the partial derivative of x of the function with respect to theta naught. So that will give us 2 theta naught, and then we'll find the partial derivative with respect to theta 1, right? So this will again give us sorry, this will be 2 theta and 2 theta 1. Okay, so right, so we'll just equate both the terms to 0, right? So this is one equation, and so essentially we'll be solving them simultaneously. So theta naught is equal to 0, theta 1 is equal to 0, and as you can confirm, the minimum of this function is 1, right? So if you plug theta naught and theta 1 both 0 to your f, so f minimum is nothing but 0 squared plus 0 squared plus 1, which is 1, right? So this is essentially an upward an upward paraboloid. Okay, so an upward paraboloid. So I have plotted this here, so maybe I'll just run this, right? So this is an upward paraboloid, right? So because now the third dimension corresponds to the f, and the 2 dimensions correspond to the 2 parameters, which are theta naught and theta 1. Okay, so essentially on this axis we can have theta naught, we have theta 1 here, and here we have the f theta naught theta 1. Okay, sorry, this is comma. Okay, so so this is how we find the minimum of a multivariate function. Okay, so in the case of, let's say, bivariate, so of course we have discussed about the gradient descent update for multivariate. So in this case, our for this particular function, for this particular f, right? So your gradient will be nothing but 2x t and 2y t, right? So this will be your update, right? So your task in your self project is to basically write the gradient descent implementation for a bivariate function. Okay, so that's given in your self project. Okay, so let's conclude. So gradient descent, as you know, is a first order optimization algorithm used to minimize a given objective function. The algorithm depends on the initial value and the learning rate. The idea behind gradient descent is that it takes a sequence of steps to go from starting position to a local minimum, right? So because this is an iterative procedure, so we start at a particular initial value and then we keep on descending to a minimum value, right? An initial value that is somewhat close to the global minimum is ideal. Of course, it's ideal, but we do not live in an utopian world. But yeah, it will not be possible for us, at least when we are implementing the gradient descent by hand, right? When we implement machine learning algorithms using the sklearn functions, so their gradient descent is already implemented in the backend, so you don't have to even bother about it, right? But you should have a very strong understanding, because this is how essentially the gradient descent algorithm is how we are training all the different machine learning models, right? So this is really crucial, and that's why I wanted to, yeah, go through this particular algorithm in this class, where you can use the concept of your calculus and linear algebra in one particular use case. So too small a learning rate makes it more likely for the algorithm to get stuck at local minimum, right? We have talked about this enough. And finally, yeah, so gradient descent is a numerical approach. So it's an iterative approach as opposed to the analytical approach. Okay. So Smriti is saying that, okay, my notepad is not visible. Okay, sorry. Yeah, so this is what I was writing, right? So for the multivariate function, sorry about it. Okay. So let me just, yeah. So should we do it for any generalized bivariate function or the given bivariate function? So in fact, you should do it for the function that we have discussed in the class, right? So that function which we discussed above, right? But I would be really glad if you can also experiment with any other functional forms. Okay, so that will be great. Just be aware, yeah, just be aware that you're using a convex function, right? So in this case, we use this particular function, but of course, I would be really happy that if you can use any other function as such, right? So that will be great. Okay. Right. So your task is to, so here, of course, see, your self project task is to see here what we did. We are only updating one parameter at once, right? But in your case, instead of writing this in this way, you'll need to write in the matrix form, where you'll be updating the parameters at once, right? So in bivariate case, you'll updating two model parameters at once, or in case of multivariate, you'll be updating multiple parameters at once, right? Because at a particular iteration, you will be updating all the model parameters, right? Does that make sense? Okay, perfect. Okay, so so this is all about the gradient descent algorithm, guys. I hope you got to learn about this new algorithm, and this is going to be yeah, it's really a crucial algorithm to understand, and I think, yeah, this is pretty straightforward too, right? So there were no difficult techniques as such. So I hope, yeah, you got to learn something substantial.